What's up?
That doesn't sound like cooking. It sounded like a gun.
Yeah, I know. It's very like a weird sound they chose for the like. Let's start.
Get ready to learn.
Yeah, get ready. All right. So just a quick review, and then we'll dive back in. So we talked about what programming is, telling a human being, telling a computer what to do, a human telling a computer what to do. And we talked about this thing called programming languages, which is effectively a tool that specifically designed to allow humans to tell a computer what to do without the human changing the way they already solve problems too much, right? Now, one thing we didn't really talk about, though, is how do human beings solve problems? I probably asked the question about, how many of you walk down the hall without bumping into any walls, that kind of stuff. And, we talked about how do you walk, that kind of crap. But if you had to generalize how human beings solve problems, how do we do it?
Use a brain most of the time.
Okay, so we're going to use our brains, and what resources do we have? So, we have all sorts of inputs and stuff, right? Go ahead.
I suppose it's mostly trial and error, but it's not always your trial and error. Use other people's experiences.
Okay. So what I try to do is I try to break it down into kind of a really, really high level version of how human beings solve problems. I like to think that we use our memory. So think about it. How many problems could you solve if you couldn't remember anything? They make fun of it in movies and stuff when people have like short-term memory loss, where every single time you meet them, it's the first time you've met them, even though that exists in real life. And that's very, very diminishing for somebody. You can't do anything if you have no memory, right? Okay, so memory is extremely important for solving problems. We need to know what we're doing, where we've been. Sometimes we need to. If I asked any of you what your name is, you're gonna, all of you know your name, right? Okay, all of us do. All right. Now, even though you're not aware of it, at some point, as he pointed out, we're gonna have to look up. We got some little storage container in our brain somewhere that has stored inside of it a variable called my name. And inside of my name is Mike. Okay, so I know that my name is Mike. And I can then spit it out. And I'm not really aware that I did that whole lookup when somebody asked me what my name is. But we can all kind of appreciate that we probably did, right? Our tongue isn't just sitting there just ready to spit out sounds at a moment's notice. We have to do a quick lookup or something like that. So we use memory. Another thing people do is we ask questions. Lots and lots and lots and lots and lots of questions. And we kind of alluded to this last time when we were talking about, I think I did use the example of going down the hall without bumping into walls. Okay. So as you're walking down the hall, you're constantly asking questions. Am I going to fall over? Am I going to fall over? Am I going to hit somebody? Am I going to hit a wall? And you're asking a zillion little questions, and you're making little tiny adjustments based on your answer to those questions. But how many of you are actually aware that you're asking those questions? We would drive ourselves insane, right? We don't hear ourselves in our head asking, question after question after question after question. But we kind of can appreciate that we probably are doing it at some sort of subconscious level, right? And making little decisions or doing something as a result of the decision of that question. So asking questions. And then we use repetition. So we like to repeat things. Once we kind of have an algorithm down, a recipe for solving some problem down, we like to repeat that. Walking is, we talked about walking, and we all agreed that it would probably be pretty close to impossible for a human being to fully articulate the details of walking. But even if we could, we all can appreciate that somewhere in our mind we've learned the pattern of walking, whether it's something that we actually have the steps, or it's, you mentioned trial and error at some point. We fell down enough times, we figured out how to balance ourselves, and then we figured out how to do that while moving, and that's what walking is. And we're not necessarily sure what all the things we have to do to accomplish that, but we kind of have learned it one way or another. Okay, so we just react. But really, walking is an act of repetition, correct? We're doing the same stuff over and over and over again. It becomes kind of like autopilot. All right, so I like to think human beings solve problems in these three broad strokes. We use our memory, we ask a lot of questions, and we have repetition. Now, something I said the first day of class, or maybe it was last class, since the first day we mostly went over the syllabus, but was that all programming languages are the same. I said something along those lines, right? Okay, so whether you've had some programming before or you've never had any programming before, it doesn't matter necessarily. It doesn't matter what languages you've had. Okay, whether you've been a Python programmer, or a PHP programmer, or a Java programmer, or a Swift programmer, they're all the same. We're gonna, over the next next couple of classes probably, we'll end up fleshing that all out. Now, when I say they're all the same, that's not really an opinion. I like to create a little slide here. I like to call this guy the mapping. 100% of programming languages provide facilities for doing these three things. Every single programming language has a way of emulating memory. These are usually through something called variables. They have a way of asking questions. This is usually through something called a conditional, or more commonly, it's an if statement. And we'll talk about why it's if statements. And then we have a way of emulating repetition through loops and procedures, /functions, /subroutines, /methods, depending on which decade you're from. All right, subroutines would be the oldest, then we had procedures and functions, and then we had methods, and they all do the same thing. They're chunks of code that we write once and reuse multiple times. All right, so 100% of programming languages give us these facilities. And if if you already know the skill of programming, okay, so you can already look yourself in the mirror and say, I am a programmer. And I introduce you to a brand new language. And you can learn how do you define and use variables, how do you ask questions, and how do you do the couple of repetition things. If that's all you learned about that language, which in most languages you can kind of figure that out in about 5 or 10 minutes, just see what the syntax for that looks like. Like, well, I know Java, and this is how you write an if statement in Java. And now I got to learn Swift. Well, how do you write an if statement in Swift? Okay, well, it mostly looks the same. Here's a little tiny little change here. I think I got it. Once I write it 2 or 3 times and reference back to this little note card, I got it. Just learning those simple things of the language, you can now solve a large classification of problem with that language you just learned 10 minutes ago. Does that make sense? So programming is the skill set. So when some of you become juniors and seniors in computer science, and I hear you complaining about, like, oh, well, you know, I like C#, but Java I just don't like. That's a very humorous statement, because, well, especially in that case, because they're really actually identical languages. But, you know, the point is that programming is programming. One language doesn't make a difference. Now, some of you will like web programming better than mobile programming, better than native programming for writing Windows applications or Macintosh applications. You know, there might be some aspect of that you find more fun in one of those than the other. But the language isn't the problem. It's just the types of problems you're solving. For instance, I hate web programming. I don't like writing web interfaces with HTML and crap like that. I'd much rather do mobile stuff on iPhone or Android. It's just, I prefer that. But the languages under the hood are the same crap. You know, they all do the same thing. All right, so these are 2 pretty important slides, kind of connecting the dots between how human beings solve problems and how programming languages, these guys, attempt to provide us a power tool that allows us to solve problems, tell a computer what to do without changing the way we already think about solving problems too much. Make some sense? All right. So we talked about 3 types of programming languages, and we're going to have a couple of slides that look kind of like this. And each one is through kind of a different lens. So this one is machine level, low level, high level, talking about whether we're going to type out zeros and ones or we're going to type out one line at a time. So we looked at a hello world program, an assembly language for Linux. So that leveraged the language that the Intel processor understands, and then also utilize the power tools that the Linux operating system provides us for writing stuff to the screen, the syswrite power tool. And we saw that even though that was a lot better than a wall of zeros and ones, it wasn't so friendly looking, right? If I promised you day one that that's what computer programming was like, some of you would probably say this maybe isn't my cup of tea, right? I mean, we all are kind of going into this maybe expecting that programming might be kind of a hard thing. But we also maybe want it to be kind of a fun thing, okay? And it will become fun. Most of you are going to be frustrated to some level, but if we start off frustrated with a high level or a low level language like that, where we're having to write these really cryptic little instructions, the fun's out the window pretty early on, right? And if it was zeros and ones that I promised you, you left day one. Okay? It's just not for us. People can't do that. We're good at other things. All right? So we like these power tools, these high-level languages, that kind of stuff. Now, when we talked about this, especially when we deal with low-level languages and high-level languages, one-to-one relationship with a CPU and one-to-many relationship with a CPU, what does that mean? When I say that a low-level language has a one-to-one relationship with the CPU, what am I talking about? We spent quite a bit of time last class talking about the nature of CPUs. Go ahead.
You type one line of code and it does one action.
Okay, one action. I kind of represented a CPU as kind of like a collection of magic tricks. So we cast enough magic tricks in a row and something real happens. So in a low-level language, every one line of code we write gets mapped to one of those magic tricks on the CPU. Where in a high-level language, we wave our hands a little bit and a whole bunch of stuff happens. We kind of prefer that power tool-y type stuff. Okay? So that's when we were talking about CPUs. I also threw in here just a little trivia thing. This isn't really part of CSC200 curriculum stuff, but when you ever see something that says an operating system is a POSIX operating system, the core thing is that everything's a file unit. So everything is going to be done in terms of file descriptors. And in today's world, Mac OS, because it's based on Unix, and Linux are all POSIX operating systems. Windows is not. That doesn't mean Windows sucks. It just means Windows has a different approach. It's perfectly fine. Windows is a good operating system. So let's talk about it from this direction. There are two kinds of programming languages. We have interpreted and we have compiled. All right, how many of you have ever heard of a compiler as it relates to programming? Okay. Okay, anybody know what a compiler is? Take a stab at it. Go ahead.
It'll take the source code for that you wrote, and it will turn it into those zeros and ones that the machine can actually run. Sometimes it'll even make minor optimizations to it.
Yeah, and I mean you're pretty much right. You let it go a little bit too far, but you're right. So it takes our high-level code, our power tool. Okay, so human beings like writing in this. Now we know that ultimately it's got to get down to those zeros and ones, one way or another. That's what the computer understands. So we're relying on a whole bunch of help in the middle. All right, so that compiler is going to take our high-level language and it will translate it into a low-level language. Okay, it won't take it all the way to the zeros and ones. That's something called a linker. Okay, extra little piece, not that important right now, but it translates. It does the conversion for us. So a compiler, just throw it underneath here. Actually, let me just throw it on another slide just so we have a separation there. Because we will be using a compiler. Actually, no, we won't in here. We're doing Python this time, so we're not using a compiler in here. Towards the end, if we start transitioning to Java, we'll be using a compiler. All right, so this guy translates a high-level language into a low-level language. Okay. It is an interpreter. A compiler is an interpreter of a type. It interprets high level into low level for that particular architecture and that particular operating system. So if we wrote system.out.println hello world in Java, it would translate it into that program we looked at last time if we were running on Linux. Not quite zeros and ones. Not quite zeros and ones. It would translate it into, do I still have it up in a tab? I don't. Let's see, Linux.
You should get rid of some of those tabs.
Oh, I'm just getting started there. Assembly.
Still read the titles. It's not enough.
No, so I do a lot of programming consulting. So this is like database stuff over here for my stuff I'm working on. But then mixed in there, here's Concordia stuff, uploading my videos. So you got
own thing?
No, this is all stuff for programming stuff. I was writing some email blasting stuff last night for a client. Let's see, Linux, hello world, assembly this guy. So it would turn that system.out.println, that one line, into something along the lines of this. Okay, that's what a compiler would do for us. Okay. Then the next step, a linker, would ultimately translate our low-level language into the zeros and ones version, which is a one-to-one mapping, right? We're just going to say, okay, well, this one line, move, is this instruction. It's instruction 1000111. That's the labeled instruction for the move instruction on the Intel processor, let's say. So replace that word with those binary bits. Okay, let's go back here. So that's what a compiler does. So we have two different kinds of programming languages. We have interpreted languages and we have compiled languages. Now, an interpreted language we want to think about as being relatively slow. A compiled language we want to think about as being relatively fast. Oops, sorry. I was plagiarizing off myself. Okay, we want to think about it as being relatively fast. Now, I say the word relatively because computers are really, really, really fast. A human being, for 99% of programs, isn't going to be able to discern the difference in speed between an interpreted language and a compiled language that's solving the same problem. Okay? Because most problems are not overly complex to the point that it's taxing our processor at all. Okay? We don't know the difference between 2 microseconds and 11 microseconds.
But we won't be able to notice.
No, we won't notice as a person. Okay? As a person, we won't know, let's go 2 and 10. So 5 times faster, we won't feel that as a person. We can't discern those types of things. But we know the difference between 1 minute and 5 minutes, right? We'll feel that. So when you do something, even if it's a little bit faster, but you do it a billion times, that starts adding up. Now we start feeling it. So some applications, every now and then, will stumble upon a problem that we're solving that's doing just tons and tons and tons of number crunching, and we will feel the difference between an inefficient solution or a solution with a slower language versus an efficient or a solution with a faster language. Only in those cases does it actually make a real difference. That makes some sense? Okay, so most of the time, it doesn't make any difference, whether it's a slow language or a fast language, relatively speaking. But every now and then, a good example being the video game world. Okay? Video games, we keep wanting them to be more realistic, more explosions, maintain frames per second, right? So you guys, you're a gamer, right? You a console or a PC gamer?
A bit of both.
Bit of both. Okay, so you probably have a decent graphics card in your PC.
Surprisingly not.
Or you dream of having a decent graphics card in your PC. All right. Anybody in here spend a bunch of money building out a gaming PC with a super fast graphics card in it? Okay, so you got an awesome graphics card in it. So he doesn't, sold his car, got a graphics card.
What's the difference? Is there really a big difference between PC and console games?
Oh, absolutely. So if you're writing, so let's take, we have 10 PC computers in here for writing games for PCs. So 10 of you have a PC that you play video games on. We probably have 10 different graphics cards, right? Each of those graphics cards has a different kind of performance. So his graphics card is kind of like Usain Bolt. Okay, his graphics card is kind of like me on the track. All right, so a little bit quicker than Usain Bolt, but we're about the same speed. We had a debate last semester about how much of a lead I would need to have on Usain Bolt to win a race. Like I'm thinking right by the finish line. But you got to give me the little extra wiggle room because he's going to have a much faster reaction off the line. There's going to be catch-up time before I even start. But all right, but so relatively speaking, he's got Usain Bolt, you have me. I'm sorry. you backed the wrong horse, okay? Now, but you guys both expect to play the same video games, right? Now, what have video games today done to combat this? You can tune the graphics, right? Okay, he can turn everything up on ultra. Okay, you have everything on black and white. You're basically experiencing still frames. Okay. Again, I mean, look, you get a job, dude. If all you can afford is me as a graphics card, you've got problems. Right? So on PC gaming, we have this big range of graphic performances in kinds of computers. Okay, so when a video game maker is writing a game for PC, they have to hit this huge audience. They want to make the ultra guys. I mean, this guy spent a bunch of money on his graphics card. I mean, he doesn't want the game to look like crap. He wants him to push his graphics card. He's excited when a game comes out and he can't quite run it on ultra. It's like, well, now I gotta sell this and sell blood, maybe a kidney, and I need to get the next best graphics card, right?
How much do graphics cards usually cost?
Oh, I mean, probably the top gaming graphics card today is, I mean, over $1,000. Yeah, I mean, they're expensive. They can get expensive. And then, I mean, you don't do you just have one, or you have them. Oh no, so he's really middle of the road. I was mistaken when I said Usain Bolt. Okay, he's more like a Concordia track runner. Okay, we might have some fast ones at Concordia. I don't know, but I assume we don't have an Usain Bolt here. Is that fair? I mean, I don't even know, but probably not. It's at least a fair bet. You know, some people get, the $1,000 graphics card, and they get 4 of them. They connect them all together. All right, it's like, now I got 4 of those because they couldn't fit all the stuff in one. Okay, so now my computer is indeed a fire hazard. All right, so bottom line is these game makers are targeting a whole bunch of different hardware when they write these games for PC. Now, when you're writing a game for a PlayStation 4, they all have the same graphics cards. Now, that's less exactly true today than it was years ago. If you had a Nintendo GameCube, every single one of them had the exact same graphics card in them. Today, if you had day one PlayStation 4 versus a year and a half later PlayStation 4, I think they made a couple of little improvements in the graphics card. And then if you get the PS4 Pro, it has a better graphics card in it. But we're not talking about the range of differences that exist in PC, because at that point Sony has control over what they're putting in their hardware. Where when you have thousands and thousands and thousands of computers out there running different graphics cards, the game makers have no control over what these people are running. So when you're writing a game for a PlayStation or for an Xbox, you have a much tighter audience that you're writing it for, a much more controlled experiment. All right? Whereas when I'm writing a game for PC, I want to push his graphics card because I don't want him coming back pissed off saying, hey, I spent all this money on a graphics card. Why? But at the same time, I want his money. So I want him to be able to play the game. So he needs to be able to tune those graphics down so that it'll be playable on his Mike Littman Sprinter graphics card. Make sense? All right, so now, what kind of frames per second do you get? 80 to 120. Okay. And that's consistent, right? What's the highest you've ever seen? 144? He knows like these. 144.2. So, and obviously if you turn the graphics way down, you get crazy numbers, right? All right. Now, what's interesting though is, there's some argument about this, but the human... Well, unless you have a super fast graphics card. Yeah, I mean, here's what it comes down to. When you watch a video, when you're playing a video game, it's like watching a movie. Okay? The human eye can only see so many frames per second. Let's just give us a round number and say the human eye can see about 40 frames a second. That's what we can roughly see. Some people can maybe see a little more. Some people can see a little bit less. When you start talking about the difference between 40 and 80 frames a second, there might be a smoothness perception thing that we feel. But generally speaking, 40 frames per second is what a human eye can see. All right? So if he's running at 140 frames a second, okay, he's clearing what a human eye can see by 100 frames per second. Okay? He's 3 times faster than what a human eye can see. Does that mean he wasted his money? Okay? Does that mean he spent all this money to do something that until we've upgraded our eyes, okay, until we get the Terminator eyes, that his graphics card isn't worth it? Is that it? Why does he have the super expensive graphics card? It's not for the average case. So the worst case. So if you're in a video game, even on his crappy graphics card, he might be in the video game and it might be reasonable most of the time. And all of a sudden, he walks into a really crowded town. Or he walks into a fight going on with lots of explosions and stuff like that. So all of a sudden, he goes from 50 frames a second down to 2. Okay? And he's watching a slideshow. Okay, it's updating every 30, 40 seconds. And by the time it comes back under his control, he's dead. Right? Or sometimes shockingly still alive. Does that ever happen to you? Like, I can't believe I survived that. That shouldn't have happened. Okay? But now he's cruising along at 140 frames a second. And he drops to 75. Barely noticed. Barely noticed. Because he had the horsepower to hold up to those giant explosions and stuff like that without dropping below what a human can really notice. Every now and then he might notice slight choppiness as it's really coming under the strain that's dropping the frames per second. He notices that little shake. Okay, there's a shimmy, that perception of smoothness between frames. But he doesn't notice the slideshow that you did. Okay, his can handle it because he has the expensive graphics card. That's the difference, right? That's those folks who spend all this money on the graphics cards. They're spending all this money for that, let's call it, I suppose it depends on the game you're playing, but let's call it 10% of the time when you need it. 90% of the time, you can get away with way less. Okay? But that 10% of the time, when he's watching the slideshow, he's still playing the game. Make some sense? Or with Xbox and PlayStation, you're in a controlled environment. You don't have the option to swap out a new graphics card in your PlayStation yet. You're probably, your next iteration of some of these game consoles, you might be moving towards something like that. Especially now that we have external graphics card type setups and that kind of jazz. So we'll see what happens.
A lot more expensive for PC.
Huh?
You waste a lot more money on PC.
Well, waste is a relative term. Depends. I would say most die-hard gamers would be PC gamers. And that would be probably a pure truth if we didn't have the advent of the esports. Because with the esports stuff, like the people who play professional League of Legends and stuff like that, you almost need kind of that lowest common denominator. Because all of a sudden now it's not about skill, right? If he's playing a video game against you and let's say you both have equal skill in the game, but you walk into the wrong area at the wrong time, he's better than you now just because of the money he spent on his machine. Where if you're both running stock PS4s, you both have the same, it's skill versus skill. So esports has kind of made our consoles still fairly relevant for things. And I think, I'm not an expert in this, but I'm going to go on a limb here and say some of you probably follow, especially after I read some of your intros on Slack. I think we have somebody in here who said they're a Dota player, and I'm sure we have some League of Legends players in here. So you probably watch the League of Legends World Championships and all that jazz. I'm assuming that there's kind of like a computer configuration. They're all playing on the same machines, so it's an equal playing field. And I know I've seen this like in the StarCraft championship stuff, that every now and then there's actually a game glitch where they'll actually reset the game because of an unfairness detected or something like that. So console games are still fairly relevant, and certainly in PC gaming, they have to give us some sort of consistent playing field. But when we're talking about playing our games at home, his computer and his computer are not created equal, right? I mean, it's just the way it is. So it's not really a waste of money. It just depends on where you spend your money. I mean, he probably sits in front of his computer a good number of hours per day. He's going to throw enough money into it where maybe she's a tennis player. She probably has 2 or 3 rackets and probably has some extra grips in her bag. The string that she likes to use in case she breaks a string, she's able to run over, hand somebody the racket with the string she likes to use so they can restring it. So that's where she spends her money is on that stuff. So it's all relative. Okay, so again, we have 2 kinds of languages: interpreted languages, which are relatively slow, and compiled languages, which are relatively fast. That relatively slow versus relatively fast thing only matters sometimes. Okay, we'll talk more about that as we get into it. But does that make some relative reasonable sense right now? Okay. Then we're going to say actually, let's do two kinds of programming languages. Hey, is it gonna fix it? Two kinds of programming languages. We have domain-specific languages, and we have general-purpose languages. So sometimes the computer, so far we've been referencing our computers as being our general-purpose computers, whether it's our desktop Windows machine or our laptop Windows Mac, whatever. These are general-purpose computers. We have these guys, and we expect that these machines can do a bunch of different stuff for us, right? So he writes his term papers on the same computer he's playing a video game on. All right. It's a general purpose machine. Now, we all, even though we're not necessarily aware of it on a daily basis, it's kind of beneath us, we don't think about it, we all can kind of accept that there's kind of computers all around us and different things. Our dishwasher has a computer of some sort in there that handles the cycles and that kind of stuff. And we can assume that that guy is probably a significantly simpler computer than this guy is. That doesn't mean it's a crappy computer. It just is solving an easier problem. It has to have less transistors. That instruction set on whatever the processor is inside your dishwasher is much, 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 much smaller than our general purpose instruction set that lives inside of our Intel processor. Okay? Because we're not writing hello world programs for our dishwasher. We're not writing video games for our dishwasher. I should say we're not writing them yet. Although it is interesting because this is the new MacBook Pro and it has that magic bar thing at the top that seems to be a waste of time so far. So it's it's a touch screen thing that's replaced all the function keys and it just changes depending on what I'm doing. Well, you can write software for that, and people have made video games. Let's use that term loosely, but they've made games that you can play on the little touch bar. Like for 2 seconds. Like, are you going to sit there for, you might.
No.
But maybe. You kind of have that look, like you might.
I would try it.
Yeah. For a prolonged period of times.
No.
You were a Flappy Birds guy, weren't you?
I was.
Yeah. I'm getting the vibe.
Yeah,
What was your Flappy Bird record? Oh, no. You know what it is. Now he's like playing it now. It's like, oh, he's got me. It was like 200 something, wasn't it?
No. Oh, no.
Really?
What?
I had like 147 on Flappy Birds.
What's
I
Flappy
was at
Bird?
like 15 minutes.
Really?
Well,
You know what Flappy Birds
15
is?
minutes over
I don't know.
Oh, so you've lucked out in life.
Wait, is it?
Flappy Birds was a game for was it just for iOS or was it for Android too? Android too. So it was a game where you had this. Oh, he's got it. That's Flappy Birds, and as it went, you tapped the screen and the bird would it would move and you had to get him to go through these little obstacles. It's mind numbing. And it was like all over. This guy made zillions of dollars off it with ads. Yeah, it was all over. And then the guy, who knows what happened with that guy?
Nintendo sued him for Mario Kart.
Oh, yeah.
Oh, yeah,
I heard he pulled it off because
They
he
tried to get him.
Well, he said he pulled it off because
he
he.
got like death threats and he felt really bad that people were like ruining their lives trying to set
Yeah, I'm
records.
sure his bank.
So-
I'm sure his bank account felt bad.
Trying to get phones, but it's still on it.
Yeah, too.
I still have it on mine because you can't get it on the App Store anymore. Actually, there's a bunch of clones up there.
Yeah. Well, you can also go back into your app history and just.
Oh, you can still re-download it. Yeah, but there was a market.
As long as you previously had it on your phone,
Yeah.
you can still get it.
And why do you know that? And why were you able to bring it up so quickly? What's your record?
Like 143.
Is it like 143 or is it exactly 143?
Probably exactly, but I don't know.
When was the last time you played it?
Just now.
When was the last time you really played it?
Uh,
Beginning of today's lecture, the first 15 minutes.
Last summer.
Oh, okay. All right, so let's keep trucking. So, anyways, we have our for our dishwashers and stuff like that. We have probably domain-specific languages for controlling those much simpler computers that don't do that many things. That doesn't mean they do unimportant things. They just do less complex things, right? Okay, so if you're somebody who's out there, and you're servicing a dishwasher, you have a little machine you hook up to it. You might feed it some instructions to have it reset some cycle or something like that, and that's a domain-specific language. All right. Our general purpose languages are the languages we usually use as computer scientists. Okay, so these are the languages that are solving large classifications of problems. We're writing video games 1 second, we're writing business applications another second, we're writing stupid hello world applications the next minute. Okay, they're built to solve all sorts of problems. And with that in mind, they're much, much, much larger languages. Now, with that in mind, we don't memorize the entire language. Okay, and this should be familiar to us. So most of us in here have been speaking English for all of our lives, right? Yeah. So we got, English under our belts for 17, 18 years, 19 years when we first started, babbling and stuff like that. Now, how many of you in here know the entire English language?
No.
You flip through the dictionary and every single word in there, you know what it is.
No.
None of it. Well, some of those smelling meat kids. There's some studying going on there, but generally speaking, none of us know the entire English alphabet, right? Well, we know the alphabet. We got the alphabet down, okay? But we don't know all the words in English. It's too big. Does that mean that we're failures in English? Does that mean we can't communicate in English? We use the tools we have available to us, right? Some of us use bigger words than other words than others. Because those are the words that we're comfortable with.
Doesn't English keep expanding every year?
We have the made-up words, right? Every single word, that's why we have, isn't there a website for, what's it called?
Urban Dictionary.
Huh?
Urban Dictionary.
Urban Dictionary, yeah, that has the new made-up words and what they mean.
Aren't all words made up technically?
Well, like the new made-up words. Yeah, but yeah, you're right. All words are made up at some point. All right, so, think about programming languages kind of through that lens, though. That we all consider ourselves fluent in English, right? Yet none of us claim to know all of English. The same thing's true in our programming languages. I've been writing Java code. Well, I've been programming since I was 9. I've been writing Java code since it came out, which was in 1994, maybe? 1994, which I'm guessing is before most of you. All of it, how long ago was 94?
20.
So before most of you. So Java's older than most of you. Okay? So I've been programming in Java since it was invented. What percent of the Java language do you think I have even seen?
20%.
Thinking something like that. That I've seen. I've probably used less than 10% of the language. But in flipping through stuff, I'm gonna count seeing it that my eye saw the name of a class at some point. Okay? A very small percentage of it. I've only been exposed to the portions of the language that have been involved in the problems I've solved using Java. All right? Now I know the core language, probably 100% of it, or very close to 100% of it. Okay? But you have a huge surrounding set of power tools that are built into Java for it to solve general purpose problems. All right, so for instance, if you are writing something that needs to encrypt passwords, you don't have to reinvent one of the password encryption algorithms. Java has RSA built into it. So you go and find the RSA encryption library, you create the object, you pass your string to it, and it encrypts it. It's the power tool that came with it. It's like your own Home Depot just sitting there. Okay? So programming languages are just like our natural languages. We're never going to learn all of it. So what we need to do is we need to learn the skills so that we can apply things that we haven't learned, haven't previously seen to a current program. Because pretty often, you're going to run into a program, at least early on in your programming days, you're going to run into a problem that you need to expand your current knowledge in order to solve. And you want to have the tools under your belt so that you can go and find, oh, this is the tool I need to use. This is the piece of Java that I need to use, the piece of Python that I need to use. And based on my previous experience, I need to be able to take this and integrate it into my software. Now, you can do that in English, right? You could flip open the dictionary, randomly pick a word, look at the definition and have a decent chance of at least being able to understand the definition to the point that you can then integrate that word into a new sentence. It might not be part of your daily vocabulary yet, but in a moment's notice, you could then produce a sentence that uses that word, correct? And you're leveraging your knowledge of English to do that, even though you were just introduced to the word a second ago. Make some sense? So programming is like that. You're never going to be asked to memorize a programming language. You will accidentally memorize large portions of the language, just like all of you, as you go through your daily lives, you're not constantly pulling out a cheat sheet for, how to ask where the bathroom is, right? You've used the phrase enough times that it's common knowledge to you now, right? Same thing's true. As you write software, you're going to be using the common tools for variables, here's the mapping thing, for conditionals, for loops and writing procedures. Those are things you're going to use all the time, and after you've practiced it enough times, remember last time we kind of referenced that computer programming is kind of like a sport? I think I mentioned that, right? Okay. After you've practiced it enough times, you're not going to have to go and look it up. It's gonna be second nature to you, right? But that's where putting the time into your homework is going to come in, because you can't just memorize programming and say I'm going to be good at it. She couldn't just go out and study tennis and then walk out on the court and win a match, right? She might know all the things she's not very good at as she walks out on the court, but you can't just study it. You have to go and practice it and do it and all that jazz. Okay, so domain-specific languages, general-purpose languages, relatively small, relatively large. This is actually going to be 3 kinds.
So there's probably 7 programming languages now?
7 programming languages? Oh, there's way more than 7 programming languages. Each one of these slides that kind of has the same topic is looking at languages through a different lens. Okay, so this one's looking at the lens of the size of the languages. This one's looking at the lens of the nature of how the languages actually end up running on the computer, that kind of stuff. So this one is looking at the, the semantics of the language. So we have 3 kinds of programming languages. We have functional languages, we have procedural languages, and we have object-oriented languages. Now, I'm not going to spend very much time talking about functional because it kind of maybe breaks our logic down a little bit here. It's a rarely used but very important type of programming, often used in like artificial intelligence. One of the kind of a popular functional languages like Lisp or Scheme. We actually use Scheme in CSC200 that I teach here, which is our programming language theory class. So we use a functional language to write our own programming language. So we create a programming language from scratch. And the reason we use a functional language is because functional languages by nature tend to be very, very tiny, concise. So they don't do that much by themselves. So you pretty much have to build everything out of them. It's kind of like Legos. So we use Scheme to write a language that's more like Java or Python. All right. So we can think if you have a graphing calculator, there's a functional language on your graphing calculator where everything is defined in terms of functions. We can take the sine of the cosine of the tangent of 45, for instance, where we got one answer here, which gets passed into this guy, which gets passed into this guy. So functional languages, you call functions inside of functions inside of functions. That's just their nature. So kind of forget about that. I won't test you on anything dealing with functional language stuff in here. Okay, the procedural versus object-oriented stuff in here, that's really our sweet spot. So the best way to explain procedural versus object-oriented is through an example. We are done at 55, correct? Okay, good. Now, I think I'd asked this question before. How many of you in here have had some programming experience before? I assume you've never had any. So those of you who have it, you're not at a disadvantage. All right, I like how everybody just raises their hand like halfway. All right, so we got like 6 people or so who've had some programming stuff. How many of you have heard the phrases at least, or the terms, procedural and object-oriented? Most of you have probably at some point seen the phrase object-oriented, right? At some point in time. All right. So who in here has seen the phrase procedural, the word procedural before? Do you know what it means? What is procedural? You've had a class with me before, so you've seen this example, so you don't get to answer. All right. So our older languages are procedural languages, and let's actually start that slide, because one thing I like to talk about is the evolution of languages. How do we get to where we are today? Understanding why didn't we just create a programming language years ago and just stick with that one? Like, why do we need so many different programming languages? So now, while this wasn't the very first programming language, it's the first one that I like to start off with here. So I like to start off with the C programming language. The C programming language is roughly, this might not be the exact year, but something in the ballpark of 1968, a couple days ago. All right, and this guy is a procedural language, whatever that means. Okay, now the best way to explain procedural versus object-oriented, typically, and actually let me go ahead and throw our second language on here, just so we can see our evolution. So this is C++. And C++, this is again a ballpark number. I think it was something in the ballpark of like 1983-ish, something like that. And this guy was object-oriented. Okay, so somewhere between 1968 and 1983, we decided that we need something better, whatever that means. Now, do you perceive that an object-oriented language is very different than a procedural language? Does it seem like that's probably a pretty big jump?
Yeah.
I mean, the perception might be that it is, right? I like to explain procedural versus object-oriented languages through an example. I like to use telephones for the example. So in our last few minutes here, let's say you walked into the room and on this table over here, I had a giant pile of wires. And I tell you that that's a telephone. Now, most of you are not going to recognize that as a telephone. Like if I started off by saying, tell me what that is. Everybody's looking at us as well, it's a pile of wires is what that is. Okay. But I eventually tell you it's a telephone. So you come over, you investigate it a little bit, you find a handset, you listen to it, you hear the dial tone, like as if that exists anymore. But we've been around long enough now that we know what dial tones are. All right. So, you upon investigation, you're finally convinced that in fact that is a telephone. It's not a pretty one. It's not like a telephone you've seen before, but in fact it's a telephone. That's a procedural telephone. All of the details are exposed. All of those wires that we all know are important, that some smart person had to put in there and get it all hooked up the right way to make that phone work. But it's all exposed. We see it all. We have to root through all the details to get to the pieces that we actually need to use to make our phone calls. That make sense? A procedural language is like that. It doesn't give us tools to hide the details that we don't need to use on a daily basis. Everything is exposed. And that was okay for a long time, because do you think the problems we solved in 1968 were a little bit simpler than the problems we solve today? Or solved in 1983? The telephone there wasn't so many wires, right? If you only have 5 or 6 wires, it's not that big a deal. That you hide that behind the TV and you're just going to say, I don't need wire management. That's okay. But as the problems got more and more complex, we needed something more. Now, the object-oriented telephone looks like a telephone. We all believe that all those wires are still there, right? We know they're stuffed inside of that box. But what do we see? We see the handset, the part that we need. We see the buttons. So the pieces of that telephone that we need to interact with on a daily basis are exposed to us. That's an object-oriented language. The difference between procedural languages and an object-oriented languages is a piece of Tupperware. It's one bucket of organization. That make sense? And we can poke holes in that bucket and have the buttons pop out and the handset there, and all the details are hidden inside. If we needed to get to them, we could spike that telephone on the ground and get to those wires. But usually we'll just go to Target and buy a new phone. Make some sense? All right. For your homework, we have read up to 1.2? 1.4. Okay. So let's go to 1.7 for Monday. Okay. Again, I'll threaten a quiz. I actually did mean to give a quiz today. I forgot. So my threats are potentially real. Just go with that. All right, and we'll pick up where we left off on Monday. Have a good weekend and watch the Super Bowl or whatever you're going to do, blah, blah, blah.